Okay, so recall then that the pullback of this part of the diagram. Okay, so let's just recall then what a pullback square is. So if we have this sort of part of the category, this diagram circled in green, then the pullback of this is essentially the limit of this sort of diagram here. So it consists of an object A and then these arrows into the objects in this diagram. Now, I mean, technically there should be 3 arrows, but we don't bother drawing the one that goes from A to omega because its form is inferred by. Now, I mean, technically, if we're talking in the kind of strict language of limits, which I was discussing in my video on limits, there should actually be 3 arrows coming from A. There should also be an arrow from A to omega, but that the form of that arrow is implied by what's here. I mean, that arrow from A to omega, if we drew it in, it could be written as phi of alpha after alpha, or equivalently as T after exclamation mark A. Okay. And the point is that we have all these arrows and things commute. So in particular, this implies that phi of alpha after alpha is equal to T after exclamation mark A. And the other important thing is that if we have any other kind of candidate for being the pullback, so anything, another object, let's say, which also has an arrow, let's say an arrow little x and an arrow r. Well, actually, let's say this object is called T, let's say. Well, in fact, in this case, we don't have to call this arrow at the top right R. We can call it exclamation mark T because it's this unique arrow into the terminal object in this case. And if we have such a sort of pullback candidate, which also has the property that phi of alpha after x is equal to T after exclamation mark capital T, then there's going to be a unique sort of intermediary arrow K, which by composing K with these sort of black arrows in the pullback, we can make these solid purple arrows in this kind of pullback candidate. So in particular, we'd have that there's this unique arrow K such that little x is equal to alpha after K, and exclamation mark T is equal to exclamation mark A after K. All right, so this is really the kind of standard view of a subobject classifier, is that for any monomorphism, there's going to be this unique sort of classifying arrow, phi of alpha, such that basically if we pull back this truth arrow, this arrow T, along phi of alpha, then we get this monomorphism alpha, which we're interested in. Okay, and I mean, this language sort of pulling back this arrow T along phi is basically just the same thing as saying that there's going to be a pullback square where, you know, this object A is really the sort of main object of this pullback, the main kind of new object that we get by solving this pullback problem. And alpha is going to be one of the sort of 2 arrows from that into the structure that we're making a pullback of, the other one being this arrow into the terminal object. So, okay, this is what we're aiming for. Now, we're actually going to show more than just that. We're going to sort of uncover some of the interesting results about topos theory and category theory, and really understand a fair amount more about monomorphisms, and also about sort of how we can find the sort of inverse image of an arrow. Okay, so this is all going to be fairly interesting stuff, I think. Certainly very useful. So firstly, let's just talk about monomorphisms. So monomorphisms are very important in category theory, especially in topos theory, because they essentially represent these sub-objects. And so it's very useful to notice wherever monomorphisms arise. And one place they arise is as arrows out of a terminal object. So in general, in a category, when we have an arrow, let's say theta, which has as its source, it has a terminal object, that arrow is automatically going to be a monomorphism. So why is that? Well, remember the definition of a monomorphism is that if we have two parallel arrows, G1 and G2, going into the sort of source object of our arrow, of our monomorphism, then we're going to have the property that if it is the case that theta after G1 is equal to theta after G2, then it has to be the case that G1 equals G2. That's the sort of defining feature of theta being a monomorphism. Okay, and in this case, where we have arrows, where we have an arrow theta coming out of a terminal object, it's quite trivial to see that this theta has to be a monomorphism. Why? Well, because if we have any two kind of parallel arrows, as in arrows going from the same arrows with the same source and the same targets, arrows G1 and G2, if we have any such parallel arrows, and then we compose, if we have any such parallel arrows that we could compose theta after, then those two parallel arrows have to be going into this terminal object. But we know from the definition of a terminal object that from any objects, there's only exactly one arrow going into the terminal object. So it must be the case automatically that G1 is equal to G2. So, I mean, the usual thing about a monomorphism is that, you know, if this composed with this equals this composed with this, then this has to equal this. But when we have these arrows going into a terminal object, we just automatically get that this equals this. So trivially, this theta has to be a monomorphism. Okay, so now let's get to something a bit more substantial, which is the definition of an inverse image of a monomorphism. And hopefully this definition is going to remind you of our definition of a subobject classifier, because it's essentially just wrapping up part of the definition of a subobject classifier in a kind of separate definition. But it's actually also useful for other things. So let's say we have a monomorphism. Let's say we'll call it J, okay? And it's a monomorphism from an object A to an object X. Well, we say that that's the inverse image of another monomorphism, let's say I, which goes from an object S to an object Y. We say that J is the inverse image of I along an arrow F from X to Y. When we have this condition that for any X, for any arrow little x, we have that X is in J if and only if F after X is in I. So this is really the picture which we're interested in here. And so what we're basically saying is that this J here is considered the inverse image of this monomorphism I along this arrow F. I mean, this is basically another way of saying that we get j by kind of pulling back I along f. In fact, that's what I'm trying to work up to a proof of. But yeah, that's basically what we're saying, is that, and we're saying that this is the case precisely when we're going to have that any arrow little x from any object t is going to be in J if and only if f after x is in I. So just remember what this word in means in this context. What it means is that, so when we say that x is in J, that means that there exists a unique arrow k such that x is equal to j after k. And what we're saying is that we're going to have that x is in j if and only if f after x is in I, in the sense that there's going to be some sort of dotted purple arrow here, such that I after that is going to be f after x. Okay. So what we're going to see, in fact, let's see it right now, is that the definition of a subobject classifier can be restated in these kind of terms. So let's just see that now, because it's not hard. So basically, we have a look. So basically, if we have a look at this definition of a subobject classifier, which we've already used, I mean, I've already read this black bit a couple of times. The important part that we're going to replace is this blue bit here. So the thing is that for this monomorphism alpha, there exists a unique classifying arrow phi of alpha, such that we have x is in alpha if and only if phi of alpha after x is equal to true after this arrow from the terminal object. So a sort of another way to say this second part here is that x after alpha is actually in this true arrow. So what we're basically saying here is that x is going to be in alpha, in the sense that there exists a kind of k such that alpha after k equals x, if and only if phi of alpha after x, so that's this kind of arrow we get by composing these two together, if and only if this is in this arrow true here, in the sense that there's this kind of connecting arrow existing. The other thing we can do, just to sort of alter this definition slightly, is to note that this arrow here, this true arrow, has to be a monomorphism for the reason that I just gave, because it's an arrow from a terminal object. So we can write this kind of V-backed arrow to denote that this T here is itself a monomorphism, this true arrow. Okay. Now let's just modify this definition a little bit. So we can rewrite it now using this new concept of inverse images. So it's basically just the same as before, except I'm noting that this true arrow is a monomorphism, and that text which was in blue, and that text which was in blue before, I've now replaced with this text in red. So now our unique phi is going to be such that alpha is going to be the inverse image of t along phi of alpha. So what I'm basically saying, I mean, I'll kind of build up to the explaining this properly, but what I'm basically saying is that if we kind of pull back this true arrow along this classifying arrow phi of alpha, we get this monomorphism alpha, which we're interested in. But I mean, it's, just sort of make sure you're with it, that it's equivalent, saying that phi is the so the main point I'm trying to get across here is that this statement, alpha is the inverse image of t along phi of alpha, is equivalent to this statement, x is in alpha if and only if phi of alpha after x is in t. And we can see that just by looking at this definition of what it means for one monomorphism J to be the inverse image of another monomorphism I along some arrow F. Okay, because it just means exactly that kind of thing. It's just that in this definition, it's just that in this definition I'm writing a J instead of an alpha, and I'm writing an I instead of a true, and I'm writing an F instead of a phi of alpha. So basically what I want to do, like the main work, is going to be to show that we can kind of restate this statement here about what the basic main work that we're going to do is to show that this kind of definition of an inverse image of a monomorphism along an arrow can be rephrased in terms of pullbacks. And what that's going to allow us to do is to take that last kind of way of defining a sub-object classifier, which I just showed you, which is in terms of the inverse image, and kind of transform that into the standard type of definition of a sub-object classifier in terms of pullbacks. So why is this worth doing? Well, a couple of reasons. One is just because traditionally people talk about sub-object classifiers in terms of pullbacks, and so if you want to connect with the ordinary literature, that's going to help you. And secondly, maybe more importantly, pullbacks are really, really useful. Like, it turns out that lots and lots of things that you can do in category theory can be kind of explained in this language of pullbacks and their dual notion of push-outs, which we won't talk about currently. But so it's well worth understanding how these concepts relate. And so I suppose one thing is, why did I even bother defining the sub-object classifier in this other way? And why am I bothering talking about inverse images? Well, as I've already said, the reason I used this original kind of if and only if based definition of a sub-object classifier is because I just think it's simpler to get one's head around at the beginning. And then this kind of discussion of an inverse image is really a sort of intermediate step between, that old definition and the notion of sub-object classifiers. And it's also this notion of an inverse image of a morphism is also useful in its own right, because as the kind of terminology suggests, this notion of an inverse image is just useful for understanding general arrows in categories. Okay, so actually this idea of an inverse image of a morphism, this definition here that I'm showing came from William Levere's book, Conceptual Mathematics, A First Introduction to Categories, which is a beautiful book. And I strongly recommend anyone to read it because it's just a wonderful book. And, this definition's in here. And the thing is, the sort of reason that this notion of an inverse image would be of alternative interest, would be of sort of independent interest, is because it really tells us how to find. It really gives us a notion of sort of generalizing the it really allows us to kind of generalize this idea of finding the subset of the source set of a function, which has its elements sent into a particular subset of a target function. So what I'm basically saying is that, let's say we have a function from one set to another. And then we identify, and then we sort of pick out a certain subset of the target set. Well, then the inverse image of that kind of subset under this function is going to be the set of things in the source set which have their elements sent into the sort of subset on the right. Okay. So this is the basic idea, but if we just replace the word subset with subobject or monomorphism, then we get, an idea of what this kind of inverse image concept means. I'll just very, very roughly touch on what this means in a bit more detail. So, I mean, this is the normal sort of this is the sort of normal way that we understand okay, but for the time being, there's no need to sort of focus too much on what this notion of an inverse image is. I will touch upon the topic a bit later, but it's not really our central focus at the moment. Our central focus is to prove a theorem that I'm going to show in a moment. Before that, I just want to explain this kind of trivial lemma here, which we're going to make use of a couple of times. So I thought I might as well just isolate it as a particular kind of lemma. And what it basically says is that a particular arrow, little x, from a general kind of object t into this object capital X is going to be in this monomorphism. And what this lemma 2 says here is that, okay, so I also thought it would be useful just to state this particular lemma here, because I think this is going to come in handy in the proof of our next theorem. And so what this basically says is that if we have an arrow little x from an object t to an object capital X, and if that little x is in a monomorphism J, then there's going to exist a unique K such that X is equal to J after K. Now, the existence of such a K is guaranteed anyway, just because we're using this word in. I mean, that's exactly what we mean by this word in this context. However, the big deal here is that this has to be a unique K. And why is this the case? Well, it simply follows from the definition of a monomorphism. You see, if there was another sort of, let's say, a K dash that we could also compose with J to make X. So if we could write this is equal to, let's say, J after K dash, well, the fact that J after K dash equals J after K and that J is a monomorphism just implies that K is equal to K dash. So we can't get around it. There's only one unique kind of arrow, which is, there's only one kind of unique arrow which we can do before J to make X, since J is a monomorphism. So that said, let's move on to our main theorem. Maybe just before I get into this, I'll just go back to the discussion of subobject classifiers, so we don't lose the kind of track of where we're going with all this. So basically, what we want to do now, we have this restatement of the definition of a subobject classifier. And in red here is the bit I changed, which is to say that alpha is the inverse image of t along phi of alpha. And what I want to do is to prove that this way of defining a subobject classifier is equivalent to this, which is to say that, well, it's just the same as before, except instead of that red part at the end, I'm now saying that we have the following pullback square, okay? So just so we don't lose track of where we're going with all of this, I just want to re-emphasize, what we're really trying to do with this big theorem that I'm about to state and prove. And what we're really trying to do with it is to transform this way of defining a subobject classifier, which is to say that, we have, for any monomorphism alpha, we have this unique phi of alpha such that alpha is the inverse image of true along phi of alpha. And we want to change that into this definition. So we want to show that this definition here at the top is equivalent to this definition here of a subobject classifier, which is very similar at the start. For any monomorphism alpha, there exists a unique phi of alpha. But now at the end, we're saying such that we have the following pullback square. Okay, so I'm really trying to show that this kind of inverse image quality can be expressed in terms of pullback squares. Okay, so that being said, let's go back to this main theorem and we can read it out now. So here's our main theorem that we want to prove. For monomorphisms, J from A to X and I from S to Y, we're going to have that J is an inverse image of I along F if and only if there exists a Q from A to S, which makes this pullback square here. So we're going to have, in particular, that means we're going to have that I after Q is equal to F after J, and this is also going to be a pullback square. So for any other kind of pair of arrows out of an object which has this property, there's going to be a unique intermediary arrow by which we can make either of the sort of two arrows coming out of that candidate object by composing either Q or J with that intermediate arrow. Okay, Basically just saying that this is a pullback square. So that the kind of two arrows and object at the top left form a pullback of this stuff down here at the bottom right. Okay, so let's just prove this then. So the first thing we're going to do is to assume this statement at the top here, that J is the inverse image of I along F, and then we're going to show that this statement at the bottom holds. Okay, so just to make sure you understand, this symbol here means if and only if. So what we're going to do is show that the statement at the top implies the statement at the bottom and vice versa. Okay, so let's start by assuming the statement at the top. So assume J is the inverse image of I along F. So what's that mean? Well, we just could unpack that. It just means that X is going to be in J if and only if F after X is in I. Okay? And this is going to hold true for any arrow little x which goes into capital X. So the first thing we want to, so basically what we're trying to do here is we're trying to make a pullback given this information. So the first steps, we want to do is to sort of gather together all of the necessary arrows. So the first thing we want to do is to get all of the arrows we need to make a pullback. And I mean, we already have from this kind of statement here that J is the inverse image of I along F, we already have these arrows J, F, and I here. But what we really want to do is to, so from this statement here that J is the inverse image of I along F, we already have I, J, and F here. So the first thing we want to do is to get this arrow Q from A to S. We want to see how this emerges from these assumptions. And so the way we do it is, well, it's quite clever really. We say that since we know that whenever X is in J, we're going to have that F after X is in I. Let's think about, do we know of any arrows, little x, which have a target object? Do we know of any arrows, little x, which are going to actually be in J? Well, we do know of one, just from this discussion so far. We know that J is in J. Okay, so if we just imagine drawing J here, I mean, that goes from an object into capital X, and it will be the case that J after the identity arrow is equal to J. All right, so it is true that J is in J. And since we're assuming that we have this inverse image property, we have this property that X is in J if and only if F after X is in I. And this holds for any X. So in particular, it holds for X equals J. So what that means is that F after J has to be in I. Okay, this is just using this statement here with X is equal to J. Okay, so we have that F after J is in I. And this is probably, in a way, the hardest part of this proof. So, you know, it gets easier from here on. But we basically now know that F after J is in I. So what does that mean? Well, that means that the composition of these two arrows is going to be in I. So what that basically means is that there's going to exist an arrow, we could call it, I don't know, let's call it Q, such that I after Q is going to be equal to F after J. Okay, so now we have our Q. which actually forms this kind of commuting square, which really is our pullback, although we still have to demonstrate that. So we have that there exists this Q, and it's going to be such that F after J is equal to I after Q. And that's good. That means this square commutes. F after J is equal to I after Q. So we're kind of halfway there. I mean, what we really want to do, though, is to show that this is a pullback square. So the next thing we have to do is to show that for any other kind of candidate, which has similar properties, it has an arrow into X and an arrow into S, such that if we do F after the arrow into X, we get the same thing as if we do I after the arrow into S, then there's going to exist this intermediary arrow by which we can emulate those two aforementioned things, those two aforementioned arrows. So we have to show that. So we're going to do that step by step. So we want to see that this is a pullback square. So let's assume that there is a kind of candidate pullback. Okay, so assume that there's an object T which has an arrow little x into capital X and an arrow little r into S. And it's going to be such that F after X is equal to I after R. Okay, so we have this type of setup here. And remember, we're assuming this thing about the inverse images. Okay, so what we really want to do to show that this is actually a pullback square is to show that there exists a unique arrow K now, which has the property that J after K equals X and Q after K equals R. Okay, then we'll be done. Then we'll really have shown that this is a pullback. That this sort of black drawing here is a pullback square. And so the important thing to realize is that by the assumption of these kind of blue objects and arrows existing, we actually have already now that F after X is in I, all right, because F after X is equal to I after R. Okay, and so what that actually means is that according to our assumption, since F after X is in I, it has to be the case that X is in J. All right, we get that from this sort of assumption here. Okay, we get that from this sort of assumption here. So we know then that X is going to be in J. And so what that means, we can use our lemma too, and it's going to tell us that that means there's going to exist a unique K such that X is equal to J after K. All right, so this is good because we want there to exist this unique kind of intermediary arrow, and we need it to satisfy two conditions. We need it to satisfy that X is equal to J after K, and we've got that. The other condition we want this intermediary arrow K to satisfy is that R is equal to Q after K. That's going to take a bit more work. So in particular, we have to do some sort of, well, you could call it diagram chasing or equation consideration. So in particular, let's consider, so in particular, what we want to show is we want to show that R is equal to Q after K. So let's start by considering the arrow I after R. Well, by our assumption that these blue objects and arrows form a kind of pullback candidate, we know that I after R is equal to F after X. Now, by this kind of statement here, that x is equal to j after k, we know that f after x is equal to f after j after k. And if you remember how q was defined, or, the fact that this black square commutes, that means that f after j is equal to I after q. So f after j after k is equal to I after q after k. All right, so what? Well, the point here is that we do know that I here is a monomorphism. So if we consider this expression here, I after r, and this expression here, I after q after k, those two expressions are equal. And since I is a monomorphism, that actually means that r must equal q after k, which is what we wanted. So we're done. So now we've shown that we have a pullback square. In particular, we've shown that this black square commutes, and that if we have a blue square with an arrow x and an arrow r, which also kind of commute with the bottom stuff, which also kind of make the bottom arrows commute, then there exists this intermediary arrow k, by which the left blue arrow can be written as a composition with the left black arrow, by which we can sort of create this left blue arrow by composing k with this left black arrow, and we can create this top blue arrow by composing k with this top black arrow. So we've indeed shown that we have a pullback square. In particular, we've shown that if we assume that j is an inverse image of I along f, then we know now that there has to exist this q such that this is a pullback square. Now all we have to do is to go the other way around in our proof, and it's actually easier the other way around. So we're going to assume that we have this pullback square with this q here, and we're going to show that j is an inverse image of I along f. Okay then, so now we're going to prove the converse. So we'll start by supposing that we have this pullback square. And so what we want to do now is to show that x is in j if and only if f after x is in I. Okay? So let's start by supposing that x is in j, and we want to show that this implies that f after x is in I. So if x is in j, that means that there has to exist a k such that x is equal to j after k. All right, this is just the definition of what I mean by in. So we have this arrow little x from some object t to capital X, and now we know that there's this arrow k, such that little x is equal to j after k. So the proof now is pretty immediate, because if we just consider what f after x is, well, we can write that as f after j after k just by substituting what we know x is. And since this is a pullback square, this black square has to commute, so we know that f after j is I after q. So then we know that f after j after k is equal to I after q after k. So if we just look at this, we know that we're writing here that f after x is equal to I after this other arrow, the other arrow being Q after K. So that does indeed mean that f after x is in I, because we can write f after x as I after some other arrow, Q after K. All right, so we've done it this way around. Now, to finish this proof, we're just going to go the other way around. So we're going to now instead assume that f after x is in I, and what we want to do is to show that x is in J. So, okay, f after x is in I. What does that mean? Well, it means that there has to exist an R such that f after x is equal to I after R. Okay, so f after x is equal to I after R. Now, since we're assuming that we have a pullback square, if you think about what this condition means, what we're essentially saying is that t, together with these arrows, little x and r coming out of it, form a kind of pullback candidate. So that means that there have to exist a unique k such that q after k equals r and j after k equals x. Well, that second part, j after k equals x, is just exactly what we want, because that's just saying that x is in J. Okay, so we have x equals j after k. That means that x is in J, and so we're done. We've now shown that given this assumption that we have this pullback square, what we get is that J is the inverse image of I along F. So we're done. We've proved our main theorem. This theorem here, okay? Okay, what do we do with this? Well, the main thing we're going to do now is just do a kind of substitution. So if we just, instead of writing J here, we write an alpha. If instead of writing an I here, we write a true, and we suppose this is now an arrow from, we'll let S be the terminal object and Y be the kind of object of the sub-object classifier. And we'll let F now be this phi of alpha. Now if we use this theorem with those kind of symbol replacements, we can just use it exactly to do this kind of transformation of definitions. So if we have this kind of inverse image based definition of a sub-object classifier, we now know that this is equivalent to this kind of definition of a sub-object classifier. That a sub-object classifier is an object omega with an arrow true from the terminal object to omega, such that for any monomorphism alpha from any object A to any object X, there exists a unique arrow, a sort of classifying arrow phi of alpha, which makes this pullback square. Okay, so we now know that this is equivalent to this statement up here, because all I've done is just replace this red statement about inverse images with this new statement about pullback squares, which is equivalent because of that last theorem. It's just that here, what I was talking about as Q before, this kind of extra arrow, its form is sort of forced in this case because it has to be this unique arrow, exclamation mark A, which is going into this terminal object. But that's okay, all the logic works out. What else do we get out of our theorem? Well, we really get a new understanding of what it means to have the inverse image, because I mean I've really shown that this kind of inverse image thing is equivalent to a pullback square, Now, I mean, so far in my discussion, I haven't really motivated um, this sort of terminology here of calling this thing an inverse image. But now I've shown that it's equivalent to this thing to do with pullback squares, we can think of it in that context and really understand why the thing's called an inverse image. So in particular, let's think about the category of sets and think about this sort of scenario which our theorem discusses. So in particular, let's just think about what this pullback square means in the category set. So we have these, we have this monomorphism here at I, and in the category of set, let's just imagine that this is actually an inclusion function. I mean, when you have monomorphisms in the category set, they're essentially just injecting the elements of one set into another set. And, you know, we can always, if we want, we can, and what we can do if we want is to imagine that such a monomorphism is actually just a pure inclusion function. So we can imagine that this function I here from S to Y, all it does is it takes these elements of S and just considers them as being the same elements, but within this possibly larger set Y. Okay, so it doesn't actually change any of the elements. That's what these inclusion functions do. They just inject one set into another without altering the elements. Okay, so if we imagine that I is an inclusion function, then we can really see where this idea of where this sort of terminology about inverse images comes from. Because if we just think about what a pullback actually is, how it's defined in the category of sets, would say, well, okay, what's the situation here? Well, we have this stuff. I mean, this is what we're taking the pullback of. So we have a set X and a set S. We have a function f from X to Y. And we have this inclusion function, which is just sort of injecting these elements S into Y, but leaving them unaltered. So if we just naively write down how such a pullback works in the category of sets, we say that, well, we can think of this pullback set A here as the set of pairs of an element E from X. So we can think of this pullback set A here as the set of pairs of an element E from X and an element sigma from S, which have the property that doing F on E gives us the same member of Y as we get if we do I on sigma. But if we're assuming that I here is just an inclusion function, then doing I on sigma isn't actually going to change it. So this will actually just be sigma here. And so this set here is really going to be kind of, well, I mean, the normal way you'd think of this is you'd say that these two arrows, J and Q here, are kind of projection functions. So J of E sigma would give us E, and Q of E sigma would give us sigma. But, I mean, we're free to think of this in more flexible terms. So, I mean, really, this set here is just going to be isomorphic to simply the set of E, set of elements E from X. So here I'm writing this symbol here just to mean in, and this is in So here I'm writing this symbol here to just mean that E comma sigma is a member of this set, and this sort of semicolon here. So I'm just using this symbol here to mean that E comma sigma is a member of this set here, and this symbol here means such that, these two dots here. Okay, standard kind of set theory notation. So the standard view, if we're thinking about pullbacks, would be that J here is a kind of projection which just takes the first element of such a pair. So J of E comma sigma would be equal to E, whereas Q of E comma sigma would be equal to sigma. But I mean, we're free to take a more kind of suitable, but I mean, we're free to take a more kind of suitable view of what this pullback is, because essentially what we can think of it as, more usefully perhaps, because it's isomorphic to simply the set of members of E, which are in this set X, which have the property that f of E is just going to be equal to I of S. I mean, in this case where we're thinking of I as being a kind of inclusion function, what this is really just doing, or what we can think of it as doing, is just giving us the kind of inverse image of this function f. So if we're taking this kind of view, then we can think of J as another inclusion function. So what we're really saying here in this context is that we have some kind of a function from this set X to this set Y, and we're picking out a certain sort of, so here's our function f here, let's say, and we're picking out a certain subset of y here on the right, let's say, we're calling this S. So here's S, this is what our inclusion function's picking out, and so here's S, and then what A is just the set of elements from X which are getting mapped into this subset under this function f. So if we take this kind of view, like what I wrote in orange, then in this case J would just be an inclusion function, and Q would actually equal the kind of restriction of this function f, so that it only operates on these members of A here. So this is why we call this an inverse image. This is where this terminology comes from. Okay then, so the next thing I want to do is to, so now we understand a fair amount about subobject classifiers. There's still the issue of whether they exist and whether they are unique. And I want to tackle this issue of uniqueness because it turns out that if a category does have a sub-object classifier, then any two sub-object classifiers it may have are going to be isomorphic to each other. That's why we keep saying the sub-object classifier, because up to isomorphism, there's only one. Okay. So in order to show this, one typically uses this pullback lemma. So I want to give a basic outline as to why there's only one sub-object classifier. And so I'm going to use the pullback lemma to try and prove it. But I'm not actually going to go through a proof of this pullback lemma. It's a very famous result, so you can look it up. Basically, the pullback lemma says that when we have a setup like this, where we have kind of two squares made out of arrows joined together, as you see, well, the pullback lemma tells us two things. Firstly, it says if these two small squares are pullbacks, then so is the outer rectangle. Okay, so what that means is that composing these two arrows across the top to get a big arrow that goes from the top left to the top right, that big arrow together with this leftmost arrow can be considered to be the two kind of arrows coming out of this pullback object, and all that stuff at the top would be then the pullback of the thing we get from the two kind of arrows at the other outer part of the rectangle. So in other words, if we compose together these two arrows at the bottom, we get a big arrow going from the leftmost, we get a big arrow going from the bottom leftmost point to the bottom rightmost point, and that together with this rightmost arrow, we can think about stuff as a diagram, and then this stuff at the top left can be considered to be the pullback of it. And we have that is the case when this little square on the left here is a pullback square, and this little square on the right here is a pullback square. So that's one part of the pullback lemma. That's actually the part that we're going to be using. The other part of the pullback lemma says that if the outer rectangle is a pullback, then so is this left square. Okay. The other part of the pullback lemma says that if this outer rectangle is a pullback, and so is this right square, then also we must have that this left square is a pullback. But at the moment, we're just going to use the first part of the pullback lemma. So here we are. What we want to do is to show that any two sub-object classifiers are isomorphic. Okay. More precisely, what we want to demonstrate now using the pullback lemma, we want to demonstrate that there's an isomorphism between these two different kind of omegas. Okay, so what we're imagining is that we have one kind of sub-object classifier which has this true arrow, which we'll call T, and this object omega, and then let's say there's another sub-object classifier in our category with a truth value called T bar and an object called omega bar. So we're going to show that omega and omega bar are isomorphic, and in doing so we're also going to find out a way to convert between these two different truth values. We're also going to find a way to convert between these two different truth arrows. So this will really help us understand why these sub-object classifiers, aka truth value objects, are kind of equivalent to each other. So here's the setup then. This is what we do. Firstly, on the right, what we're doing is applying the definition of this sub-object classifier, this one with the kind of standard notation here, to classify this monomorphism here, T bar. Okay. And so according to our definition of what a sub-object classifier is, our pullback based definition, there's going to exist a unique arrow phi of T bar, which is the kind of classifying arrow from this for this monomorphism T bar. And the way that this works is that okay, so the way this works is we say that phi of T bar is this unique classifying arrow for this monomorphism T bar, and that's using this sub-object classifier on the right here. The other part of this, and so one of the implications of this then, I mean basically what our pullback based definition of the sub-object classifier tells us is it tells us that we have to have this unique arrow phi of T bar such that all of this stuff such that we have this pullback square. Okay, now what we do is we do the same thing using our other kind of sub-object classifier. So we then say, well, under this sub-object classifier, supposing it is, so we've got a different arrow T bar for true, and a different object, perhaps omega bar. And then we'll say, well, okay, if this is a sub-object classifier, let's apply it to classify this monomorphism here, T. And so again, by our definition, we get that there's a unique arrow phi of T bar, which is such that it forms this pullback square. So okay, now we can apply our pullback lemma because we have two pullback squares next to each other, these two squares on the left and right, and so it follows that this outer rectangle is a pullback. So in other words, this is a pullback. But now let's think about our definition of a sub-object classifier again, because if we just think about everything except the bottom arrow, we have that Well, we can imagine, well, we have this truth arrow here. So we have our sub-object classifier set up. And let's suppose we're classifying this monomorphism here. So there ought to exist a unique kind of classifying arrow along the bottom here, which makes this into a pullback square. Well, we already know that this phi of t bar after phi bar of t does the job and does make this into a pullback square. We know that from our pullback lemma up here. However, if you think about it, you can convince yourself that it's also true that a choice of this bottom arrow to be the identity arrow of omega also forms a pullback square. And so, since our definition of a sub-object classifier tells us that there's just a unique kind of classifying arrow along the bottom here, we know that these two things have to be equal. And if you apply a similar kind of argument with the omega and the omega bar interchanged, you get the kind of opposite result. So we also can get phi bar of t after phi of t bar equals 1 to the omega bar. So what that means is that these two arrows here are just the two parts of an isomorphism between omega and omega bar. So we really have this kind of situation. Where these two arrows compose to give the identity either way around, okay? And how can we use this to convert from one truth value to another? Well, notice that these are our isomorphisms between our kind of omega objects. And what about these arrows at the top? Well, we can rewrite this as ID of 1, the identity arrow of 1. And here it is again, the identity arrow of 1. So what this tells us then is that phi of t bar of t, just looking at this pullback square here, it tells us that phi of t bar of t, it tells us that, so if we just look at this right pullback square here, what it tells us is that phi of t bar of t bar equals t. So this allows us to get this truth arrow t from this truth arrow t bar. And we get a similar kind of connection on the left. So we can convert between the truth arrows and convert between the kind of omega objects. So now we really understand if there are more than one truth value object, or also known as a sub-object classifier, we don't have to worry because they're isomorphic and we can convert between them. So while I'm going over the technicalities, I wanted to say something else about this category of sub-objects of X. So in particular, we've been thinking about when might there be an arrow K from a subobject f of x to a subobject g of x. And I've already tried to argue in the main video that if there is such an arrow, it has to be unique. So if there is an arrow from f to g, then there's only one. But I also should say that such an arrow k itself also has to be a monomorphism. Now the reason for that is explained by this lemma here. So what this says in general is that if g after k is a monomorphism, then k is a monomorphism. Now the proof to this is quite simple. Remember, k would be a monomorphism when we have the property that k after x equals k after y implies x equals y. Well, let's assume k after x is k after y. Well then, g after k after x equals g after k after y. And since we're assuming that g after k is a monomorphism, we get x equals y. So there we have it. Okay, so what we want to do now is prove this theorem. So suppose we have two subobjects of x, this monomorphism f from a to x, and this monomorphism g from b to x. Now what we want to prove is that these two subobjects of x, f and g, are going to be isomorphic in the sense that they're isomorphic in our category of subobjects if and only if their classifying arrows are equal. So we'll start by assuming that the classifying arrows are equal. Well, in that case, we know that this is a pullback square. This just follows from the kind of definition of a subobject classifier, that phi of f is this arrow, which makes this a pullback square. And similarly, phi of g will be this arrow that makes this a pullback square, but we know phi of g equals phi of f. So we have these two things, and we know they're both pullback squares. So what we can then do is think about this pullback square involving f, this kind of standard one, and we can consider the stuff to do with b, the other kind of parts of this pullback square involving b, as a kind of candidate pullback. So then according to the definition of this as a pullback, that means that there exists this unique arrow k1, such that, because I mean, we know that this b here is going to be, we know that this b with its arrows g and exclamation mark b are going to form a pullback candidate, right? Because actually g, phi f and exclamation mark b, t really do form a pullback square, so we know that they have to commute. So we know, for example, phi of f after g is t after exclamation mark b. And so this is a proper pullback candidate, so we know that there exists this unique arrow k1, and we have that g is equal to f after k1. Okay, now we just do a similar thing the other way around, now saying, well, we have this pullback square involving g here, and now we take a with its arrow f and exclamation mark a is the candidate, and that gives us the other result that f equals g after k2, where k2 is this unique arrow from a to b, which is such that, as I say, it's such that g after k2 equals f, and exclamation mark b after k2 equals exclamation mark a. So we have these two results here, that g equals f after k1 and f equals g after k2. And then if we just think about what's going on in our category of subobjects, what that basically means is that K1 is an arrow from G to F, and K2 is an arrow from F to G. Now, since P of X is a pre-order, the presence of two-way arrows implies that these two things are isomorphic. So we know that these are isomorphic subobjects. But let's see this a bit more directly. So we know that G equals F after K1 and F equals G after K2. So we have that G equals F after K1, and then doing the other substitution, we get that this is equal to G after K2 after K1. That's just doing the substitution for G. And then since G is a monomorphism, and we can also write G as G after IDB, we know that IDB has to be equal to K2 after K1. And similarly, we can get IDA equals K1 after K2. So, these really are, K1 and K2 really are sort of isomorphism inverse pairs. And we have that F is going to be isomorphic to G in this category of subobjects of X. Okay, so now we want to prove the convert. So we've done it now. We started by assuming that phi F equals phi G, and then we've managed to show that F is isomorphic to G. Where are we now? Yeah, we've managed to show that F is isomorphic to G. So we started by assuming that phi of F equals phi of G, and now we've shown that F is isomorphic to G. Now we want to do the converse. Okay, so we're going to suppose that F is isomorphic to G, and we want to show that phi of F equals phi of G. The classifying arrows of both of these things are going to be equal. Okay, so how are we going to do it? Well, firstly, F is isomorphic to G. What does that mean? That means that F and G are going to be isomorphic arrows. That means F and G are going to be isomorphic objects in this category of subobjects on X. This category of this kind of slice category of monomorphism. This kind of subcategory of the slice category that's objects are monomorphisms into X. Okay, so we know that F is isomorphic to G in here. What does that mean? Well, what it really means is that we have the unique K1 and K2, which are going to be such that G is equal to F after K1 and F is equal to G after K2. So what we're going to do now is we're going to think about pullbacks, okay? Because the real strategy of our proof, what it's going to be, is we already know that we have this pullback square here involving F and phi of F. This just comes from the definition of phi of F as this arrow that makes this pullback square, according to our definition of a subobject classifier. And now we know we have these two other arrows, K1 and K2, which are sort of involved in this isomorphism between F and G. And our strategy is going to be to show that this purple stuff also forms a pullback square. Okay, because once we've done that, since we know that there's just a unique classifying arrow which forms one of these pullback squares, according to the definition of a subobject classifier, that means that that arrow, which would form that pullback square with this G stuff, well, we know that could be phi of G, but we're going to get, by showing that that's a pullback square of this situation as well, we're going to get that that could be phi of F as well. So then phi of F would have to be equal to phi of G, because there's just one unique classifying arrow which makes this G stuff into a pullback square. So let's do this then. So how are we going to do this? How are we going to show that that these purple arrows, the G and exclamation mark B, form a pullback square with phi of F and T? Well, we need to show two things. We need to show that that square commutes, and we need to show that given any other kind of candidate pullback, we can sort of emulate the arrows from that in a unique way. So firstly, let's just think about this black thing that we already know is a pullback square. So we know already by the definition of phi of F that this is a pullback square. Now, what's that mean? Well, it means that we can compare it with other pullback candidates. So let's consider a sort of different pullback candidate. So what does that mean? What does it mean that this black square here is a pullback? Well, the first thing it means is that this square commutes. Okay, so we know that phi of F after F equals T after exclamation mark A. We know this. We also know that if we have another pullback candidate for this situation, that is a unique way to emulate its arrows. So suppose we have a pullback candidate C with an arrow H into X and exclamation mark C into the terminal object 1. Well, then we know, and suppose this is such that T after exclamation mark C equals phi of F after H. So this causes the square to commute. Well, then there has to exist a unique L from C to A such that F after L equals H and exclamation mark A after L equals exclamation mark C. So we know we have to have this kind of situation. We know that if we have a C with a H and exclamation mark C such that phi of F after H is T after exclamation mark C, then there exists this unique L such that F after L is H and exclamation mark A after L is exclamation mark C. Okay, so what? Well, what we're going to do now is we're going to think about candidates. So, okay, we know this works for our original black square. We want to show that a similar thing works for this kind of square using these purple arrows, because we really want to show that this thing with the purple arrows involving G is a pullback square as well. So we want to show that this is a pullback square. So let's suppose that we have such a pullback candidate as I've just been discussing. So we really have this kind of situation, okay? We have this purple, these purple arrows, and we want to show that this stuff is a pullback. And we also have this pullback candidate C here. So what are we going to do? Well, the first thing we want to do is to show that this these purple arrows form a kind of commuting square with phi of F and T. So we really want to show that phi of F after G equals T after exclamation mark B. So we can do this as follows, okay? We know that phi of F after G is going to be equal to phi of F after K1. We know that because G equals F after K1. So we have phi of F after G is phi of F after K1. And we know that's going to be equal to T after exclamation mark A after K1, because this black square commutes. And we know that K1 after exclamation mark A is just this unique arrow from B to the terminal object. So we know that this is just equal to exclamation mark B. So we have that phi of f after g is t after exclamation mark b. So that shows that this purple stuff forms a commuting square. Okay, so we're sort of halfway there to showing that this is a pullback. The other thing we have to do is to compare it with this other pullback candidate C here and show that there's a kind of unique way to emulate what it's doing. So more precisely, let's suppose we have this pullback candidate C here with this arrow H into X and this arrow exclamation mark C into 1. And we'll suppose it makes this square commute. So phi of f after H is t after exclamation mark C. Well, as I was saying before, since this black square is a pullback square, we then know that there has to exist this unique L here, which is such that H is equal to F after L, and of course exclamation mark C is equal to exclamation mark A after L. Okay, so we have this stuff. Now what we're going to do is we're going to define L star, which is going to be our intermediary arrow from C to B, which we're going to use to really show that this purple stuff is a pullback by showing we can emulate what's going on with C. So here is L star in this picture. And we're going to just define it to be K2 after L. Okay, so we're just going to use this intermediary arrow we had into A and then compose it with K2 to get this intermediary arrow from C to B that we're going to use to emulate what C is doing using B. So now this has the property that we want it to have, because F after L, because I mean, what we really want to show now, we want to show that H is going to be equal to G after L star. Right, we want this arrow H here to be able to be written as G. Okay, we want this arrow H here to be able to be written as G after L star. And that's what we do indeed get, because we already know that H is equal to F after L, and we know that F is equal to G after K2, so F after L is equal to G after K2 after L, and we know that L star is K2 after L, so we have H equals F after L equals G after K2 after L equals G after L star. So that's great. And we also, so that means that yes, we can emulate this arrow of H using our intermediary arrow L star. And of course we can also emulate exclamation mark C, because exclamation mark B after L star is indeed going to be this unique arrow from C to the terminal object, so it has to be equal to exclamation mark C. So we know that there's an intermediary arrow from C to B which can sort of emulate the effects of H and exclamation mark C. But how do we know it's unique? Well, the way we know it's unique is just from the properties of a monomorphism. So if there is such an arrow, L star, then it has to be such that H is equal to G after L star. And we already know that H here So, and we already know that H here can be written as F after L, or it can be written as F after K2 after L. So, and we already know that H here can be written as F after L, or it can be written as G after K2 after L. So this equation implies that G after K2 after L is equal to G after L star. And since we know that G is a monomorphism, we have to pick L star to be K2 after L. So we have to set this intermediary arrow L star to be K2 after L. So this implies that this intermediary arrow is unique because G is a monomorphism. So that means when we have this equation, we can just kind of cross off the G's, and we know that K2 after L equals L star. So the choice of this intermediary arrow is forced. We have to have K2 after L equals L star. The intermediary arrow has to be K2 after L. So that's it. We've now shown that this is a pullback square. Okay. This square where we have phi of f after G going along the bottom and T after exclamation mark B going around the top right. Okay. Well, so what? Well, the point is that by our definition of our truth value object, our subobject classifier, we know that for any sort of monomorphism G from B to X, we know there has to exist a unique phi of G, which makes this as a pullback square. Okay, that's how our subobject classifier is defined. However, we've just shown that making a choice of a classifying arrow of phi of f also makes this a pullback square. And since there's just supposed to be a unique arrow that makes such a pullback square, and we know that phi of g can do it, we must have that phi of g equals phi of f. And so we're done. We started by assuming that f and g are isomorphic subobjects of x, and now we've got that phi of f equals phi of g. Okay, so what I want to do now is to prove this theorem, which is essentially saying that the pullback of a monomorphism is a monomorphism. So more precisely, if we have this kind of pullback square, and so we're making the pullback of this part of the diagram here at the bottom and right, and at the right we have a monomorphism beta, then if we find the pullback of this, that's going to be this object A with these two arrows, alpha and Q coming out of it, and I want to prove that alpha is a pullback, and I want to prove that alpha is a monomorphism. So we're going to do the standard type of thing and suppose that we have a couple of parallel arrows preceding alpha. We're going to call them A and B, little a and little b. And we're going to suppose that alpha after A is equal to alpha after B. So imagine these couple of arrows A and B plugged in before alpha, and we're supposing that alpha after A equals alpha after B. And our goal is then to show that A equals B. Then we'll have shown that alpha is a monomorphism. So the first thing is to note that P after alpha equals beta after Q. This square has to commute. So thinking about A and B as well, we get these four equations here that P after alpha after A, P after alpha after A is P after alpha after B, which is beta after Q after A, which is beta after Q after B. So that's these four equations here. Now, we're assuming that beta is a monomorphism. So from these last couple of equations, we get that Q after A is Q after B. Now, let's write alpha after A. So let's now write X. So now let's define X to equal alpha after A. Well, we know that's also equal to alpha after B. Let's also define Y to be Q after A, which we know is also equal to Q after B. So now, let's suppose we have this. So now, let's suppose we have this Z with these arrows, little x and little y, coming out of it. Well, we know that this is a pullback candidate in the sense that it makes this square commute. Okay, because we know from our equations up here that P after X equals beta after Y. So since this black square is a pullback square, we know there has to exist this unique K, such that alpha after K equals X and Q after K equals Y. However, it turns out that using a K equal to A or a K equal B both satisfy this condition. So since we know that this K here, this intermediary arrow is unique because we have a pullback, that means that we must have that K is equal to A and equal to B. So we have A equals B, which is what we're aiming for. So we've now shown that this alpha here is a monomorphism and proved this result.